on this table and over on that table. Tonight's images are diverse galaxies. I think one of them is called, I found it, ESO 325-G004. One of the more poetic names for a galaxy, of course. But if you would like to know what that galaxy is, some more information about that galaxy, we have a description of it on back. I guess the point of this lithograph is to talk about the various shapes of galaxies, spirals, ellipticals, and irregulars. Didn't grab it on the way in, go ahead and grab it on the way out. Tonight's talk will be 3D spectroscopy and the dynamics of galaxies. I told you he would come up with a cool name because I'd previously been listening to it just as IFU spectroscopy. But 3D spectroscopy sounds cool. Can't wait to find out what that's going to be. Upcoming next month, Mia Bova will be talking about the Harvard computers. And notice that's in quote because they are the women who did the classification, original stellar classification. An amazing historical as well as scientific story. June 6th, I do not have a speaker. I realized that yesterday. And I was like, oh, wait a minute. Because I have a speaker for June 27th. We have a special date. We do have a talk in June. Amber Strawn from NASA Goddard Space Flight Center will be coming up, and we're having a workshop at that time, and so she is going to give a public lecture associated with that workshop on astronomy in the 2020s, synergies with WFIRST. And WFIRST stands for Wide Field Infrared Space Telescope, and that is a planned mission that we hope will launch in the 2020s. So if you want more information, we have our website. If you just go to your favorite search engine and go put in Hubble Public Talks, you should find this web page. On this web page, you will find the upcoming lectures list, the links to watch it live online. If you want to, if you have to stay home and can't come in, you can watch it live online. You can watch the past lectures, both available on YouTube and the Space Telescope webcasting sites. You can also sign up for our public lecture series announcement, our emails. We send out about 2 emails a month reminding you of the upcoming lectures and telling you where those webcasts are. We have a question.
July.
What am I going to do about July? I will not be doing because we've got the June 27th, I'm pretty sure I will not be doing a July, whatever date that would be like.
Well, it's the 4th. It's the first.
Yeah, so it would have been the 11th. And since instead of moving it back a week, we're just going to move it forward a week to the 27th. Is that okay? Actually, July is one of the 2 hardest months to get speakers for. When I'm looking back over the 15, 16 years I've been doing this, I've had to fill in July and January most often. Those are the 2 months. So getting Amber to speak June 27th is actually really good for me. It alleviates trying to twist somebody's arm for July, and we'll be back in August, okay? All right, good question, thank you. Email. I just showed you how to, this is the preferred way to sign up for the email announcements, but there's other ways at maillist@stsci.edu, or if you really just want to be lazy, write it down on a piece of paper, hand it to me afterwards, and I'll make sure you get on the email list. If you would like to send us comments and questions, we have an email at publiclecture@stsci.edu. You can send us some questions. We're also available on social media. We have Facebook, we have 2 Twitter feeds, we have Google+, we have Pinterest if you are into following that. I myself have a blog on Hubble site as well as Facebook, Google+, and Twitter feeds that I occasionally do try to provide some interesting and cool science on. Tonight, yes, we do have the observatory tonight. I know it's been several months since we've had the observatory person come through, but Irini said that she would be here at 9 o'clock tonight. So after the lecture, if you would like to go out and look through the telescope across the street, please, we're going to meet down here, over here, and she'll take you across the street, okay? All right. And now my news segment, News from the Universe for April 2017. Our first story tonight. I get a kick out of you. And the kids in the audience may not know the reference, but the older folks in the audience definitely recognize the reference from the song. You probably don't know where I'm going to take this, do you? But we're going to start with the solar system, with the sun and the 8 planets pictured here. And I will add as a side note, this is not the real point of the story, that there was things about ninth planets this month. A group of astronomers tried to put together a drive to get Pluto reinstated as a planet. And the rest of the astronomers go, nah, no thank you. And there also is a scientific prediction that there is another ninth planet way outside the solar system. And one of the cool things that they just did is they did a citizen science project to analyze a lot of data, and they came up with 4 possible candidates. All right, this is news that just came out in the last couple of days. So there may actually be I believe it's a Neptune-sized planet way out there. There's some evidence based on orbits that indicates that it might be out there. We just had a talk here a few weeks ago by Mike Brown, who is the one who's leading the search for this, and we'll see. So the number of planets in the solar system, as always, is going to be maybe in flux again. But regardless of how many planets you think should be or shouldn't be in the solar system, we can agree on one thing. There is exactly one star in the solar system, okay? We have one star, the sun, in the center of the solar system. And you might think that that's typical, but it's not. Most stars are actually in multiple star systems. All right? Half the stars you see in the night sky are binary or multiple star systems, which means that about 2/3 of the stars are in multiple star systems. So for example, the North Star is called Polaris. Here is the North Star at the handle of the Little Dipper, and you hear the pointer stars of the Big Dipper that point to the North Star, Polaris. Polaris is a double star that is Polaris A and Polaris B when you look at it closely. And if you look at Polaris A even closer, you find that Polaris A is actually a double star itself, Polaris A and Polaris AB. All right? So these stars are in multiple systems. And there are 3 stars in this that are gravitationally bound here. And it's a stable system because Polaris A and Polaris AB are a tight binary. They're in real close. And then Polaris B is sort of a wide binary, far further away. Now, you know the saying that 2's company and 3's a crowd? Well, that's also true in gravitational systems. So if Polaris B were in close with Polaris A and Polaris AB, right, then the gravitational interactions of 3 objects in a tight binary would likely lead to one of them being ejected. Gravitational interactions that would tighten up a binary and kick out one of the stars. The point is that gravitational interactions among multiple star systems can dissolve the star system by sending off the stars, by kicking the stars out of the gravitational system. All right, where's this going to lead us? It is going to lead us to the Orion Nebula. This is the central region of the Orion Nebula. Here are the trapezium stars. We're not going to talk about those today. Instead, we're going to talk about this region up here. It's the Kleinman Low region, or just the KL region within the Orion Nebula. And if I zoom into it, within the KL region, we had previously known about 2 what we call high velocity stars, stars that are moving at significantly speeds across the night sky. And one of them was called BN, and I forget what that stands for. It's somebody's name or something like that. And the other one was called I. And you can't really see it in this Hubble image because it only shows up at deeper infrared wavelengths, okay? And so they saw that BN and I were moving across the sky, and they had reasoned that about 500 years ago they were together, and they're now flying apart from each other. However, when they did the momentum calculations, they found out that it doesn't work, that there isn't enough mass split, the mass split between the 2 isn't even, that the mathematics of it doesn't work out, that you could send them off in those directions at those speeds with those masses and have a conservation of momentum. So they were expecting that there has to be another component to this system. Well, they were doing another Hubble study looking for free-floating planets in the Orion Nebula. And they were comparing images from 1998 with those of 2015. And in doing so, they noticed this star here called X. They call it source X. And when they looked at the two epochs, they found that source X had a significant difference between 1998 and 2015. They then calculated that backwards to see where it was long ago, and lo and behold, source X, source I, and source BN were all around that initial position about 540 years ago. So they have found the third component, and when they do the mathematics now, they can get conservation of momentum, and so that all three of them could have been part of a single system that broke apart 540 years ago, around 1470. They said during the time of the War of the Roses. All right? So these three stars got a gravitational kick out of each other about 500 years ago. All right. Our second story tonight, supernova survivor. We will be talking about type 1a supernovae. All right, now these are supernovae that come from the explosion of a white dwarf. A white dwarf is a stellar remnant. It's basically a giant atom, okay? It's supported by something called electron degeneracy pressure. The star has burned out and it's collapsed in, and the pressure of electron orbitals pressing against one another is actually holding this star up. It's like a giant atom about the size of Earth, but weighing about the mass of the sun, okay? And if you add in order to make it explode, you have to accrete mass onto it. You have to add more mass until it exceeds what's called the Chandrasekhar limit, all right, about 1.4 solar masses. Because at 1.4 solar masses, the electron degeneracy pressure cannot withstand the gravitational force, and it collapses in upon itself and then explodes, all right? And because this is a white dwarf explosion is always going to occur at this mass, well, that supernova explosion will have a standard brightness and have a standard light curve, and they're an extremely important type of supernova for us gauging the brightness of it and therefore the distance to it, and it's useful for all sorts of purposes. It actually was instrumental in the discovery of dark energy and the accelerating universe, okay? So understanding them is important. And there are two hypotheses as to what causes the white dwarf to go over 1.4 solar masses. First one is the binary white dwarf merger. You have two white dwarfs that are in orbit around each other. They spiral in, merge together. The total mass goes over the Chandrasekhar limit, and you get an explosion. We're not going to talk about that tonight. We're going to talk about the other hypothesis, which is called a cataclysmic binary system. I just love that name, cataclysmic binaries. And what that is you have a white dwarf star here, and you have a red giant or a red supergiant that is bloated up, and the material streams off of the red giant onto the white dwarf and accretes onto the white dwarf, pushing it over the Chandrasekhar limit. So the question is, what happens when that white dwarf explodes as a supernova? What happens to the red giant or the red supergiant? Okay? Well, actually, we believe it survives. We believe that the star actually survives. I mean, of course, its outer layers are going to get blown away, but the star will survive. So we've been looking for evidence and have found what we believe are evidence of the binary star in these type 1a supernovae. The second star, it's the first star, of course, blow itself to bits. So our image that we released just recently is this one, a nice, beautiful image, featuring the supernova remnant N103b. Okay? This is in the Large Magellanic Cloud, a satellite galaxy of the Milky Way, about 170,000 light years away. Now, the supernova remnant isn't the whole image. It's actually just this region up here. This region down here is not part of the supernova remnant. That's actually part of the star cluster NGC 1850, but it's still so beautiful we wanted to include it in the image. All right, so if we close in on the supernova remnant N103b, here is the guts of the star that were blown out into space by that supernova explosion, and they have been searching this field trying to find the companion star to the type 1a supernova. They have found a yellow dwarf star, very much like our own sun, that they believe is that binary companion to the white dwarf that exploded. They do not have definitive proof yet. All right, they do not have the smoking gun that says this truly is, but they have a scientific paper out arguing why it could be, and more research will help figure it out. And as I said, the star cluster NGC 1850 in the lower corner is also really cool. You can see there's a lot of resolution in this image to see all the great details. So even though we didn't have a definitive science result, we sort of released this also as just a really gorgeous picture of stars and nebulae in the universe, one of the pretty pictures that we often release from Hubble to show you just how wonderful the universe really is. All right, and so we may actually have a survivor of a supernova existing up here in that remnant. Question?
If you had a supernova and there was a planet with life, how far from that supernova would the planet with life have to be to survive?
Yeah, that's a really good question. The estimates have ranged from 1,000 light years to 10,000 light years that I've seen, simply because the energy put out by the supernova not fry everything, but can disrupt the atmospheres, etc. And such. So I really don't know the definitive answer. I remember somebody giving a talk and discussing that here, but I can't remember. So certainly if it were 10 or 20 light years away, it would be a problem. 100 light years would probably be a problem. I think that if it's 1,000 light years, that's where we start to get into the safe. We're definitely the safe zone. But where in there that it happens, it also depends upon what energetics you're considering and about it especially. Okay, and
stars are there within 1,000 light years?
Stars within 1,000 light years. Okay, there's about 1 star per cubic parsec. I know I'm talking parsecs, which is 3 light years, but 1,000 light years is what?
300.
Yeah, 300. So yeah, there are hundreds of stars within 1,000 light years.
Okay.
Yeah. All right. Question in the back.
Just a general question about the Hubble. I read about the magnificent optics and the fantastic instrumentation. What about just the basic pointing apparatus? Are there little rockets?
Okay. So the question was, how does Hubble point? It uses reaction wheels and gyroscopes. The reaction wheels, as if you spin a wheel in one direction, the telescope turns in the other direction. So there are reaction wheels on Hubble that allow it to turn and point, and we have the fine guiding sensors and the gyroscopes to lock onto a star and have updates many times a second to keep it on the star.
Thank you.
Yes, right here.
About what distance is it between Polaris A and Polaris B?
The distance between Polaris A and B, I did not remember that from my reading this afternoon. Usually these binary systems can be anything from order of like Earth-Jupiter, Sun-Jupiter distances, which is a few AU, on up to about 100, 200 AU. Okay, so their solar system type distances. If you get too far beyond a few hundred AU, then well, if you get to thousands of AU, certainly you can get the tidal effects of passing stars to destroy systems. Okay, good question. All right, I can't answer too many questions because we gotta get to our speaker, but one more question, then I'll go.
Do Polaris A and B orbit around one another, or are they just...
Yes, so Polaris A, so the question was about describe the orbits of the system. Polaris A and Polaris AB are in a tight binary system. Okay? These two and Polaris B are in a wide binary system. So you got spinning here, and then you got the overall thing. Okay? That's how we look at it. These are a tight binary, and this is a wide binary. It ends up being a total being a triple system. Okay. Thank you very much for your questions, but I got to let David come up and do his talk. So, our featured speaker tonight is Dr. David Law from the Space Telescope Science Institute. And you will be able to tell by his accent that he was originally born in the UK, came over when he was young. He did his PhD at Caltech. followed by postdocs at UCLA and Toronto, if I remember correctly, before coming to Space Telescope about a little more than 2 years ago. He is on the James Webb Space Telescope MIRI instrument team. Actually, I shouldn't say MIRI instrument. We were talking about that. It's the mid-infrared instrument, which makes it MIRI. But if you say MIRI instrument, you're sort of saying instrument thing. But, you know, he's on the MIRI team working on the James Webb Space Telescope that will launch in a year and a half. So, ladies and gentlemen, give a warm welcome for David Law.
Let's see. Oh, sounds like the volume's good in the back. Let me just wake this up quickly. Wait for it. There it is. Okay, so as Frank was saying, then I changed the title from what you might have seen a month or so ago. I suppose I could have also replaced it with Galaxies in 3D. If you liked them in 1D and 2D, you'll love them in 3D. But while I'll spend a good chunk of the talk telling you about why I think 3D spectroscopy is cool and what it is that it's taught us about galaxies both in the near and far universe and some of the great things that I think we'll learn from it when we use similar types of instruments on James Webb, what I thought I'd spend the first part of the talk doing was to back up a little bit and say, well, what actually is spectroscopy and what has it taught us about the universe? And now, why is spectroscopy interesting before we jump into three-dimensional spectroscopy? And it turns out spectroscopy has actually told us a lot of what it is that we know about the universe and how it works today. So I can start out with a picture like this that many people are familiar with seeing out of HST. This is a picture of a nearby barred spiral galaxy, NGC 1300. If you look at the picture, you can get a lot of information just from the picture. You can see it's got these blue spiral arms. The blue color tells you there's a lot of star formation going on in those arms. There's a bar in the middle and a bulge in the center as well. The colors of that bulge, more of a yellowy, reddy color, tells you there's not as much ongoing star formation. It's more older stellar populations. There's maybe more dust in there that you can see in the dark colors as well. But how do we actually know that? How do we know I'm not just waving my hands and saying, it's blue, it's young stars, trust me? How we know is spectroscopy. So if I zoom into that galaxy a little bit, I'm cheating a little, this isn't actually that galaxy, this is an open cluster in the Milky Way, but you get the idea. It's zooming in to look at individual stars now, where you can see similar distributions of star colors, the red stars, the blue stars, the whitey yellow type stars, and our common law is that these different colors of stars correspond to different temperatures of stars. The blue stars are the very young hot stars, the red ones are the older, cooler, less massive stars. But that's using the color information here. We can get a lot more information out instead of just looking at red, green, blue, very coarse colors, if we try splitting apart the colors in a little bit more detail. That's the idea behind a spectrum. So this is the visible spectrum of light, ranging from sort of blue-violet around 400, I'll keep changing between units, 400 nanometers, all the way up to about 700 nanometers or so, which is red. This is the length of a set of light. So a nanometer is a billionth of a meter. So this is 400 billionths of a meter, is the typical wavelength of these blue lines of light that we're looking at, all the way up to about 700 or so. And if we can split the light from the stars that we're looking at up into its component colors in such a spectrum, we can learn a lot more about them than we can get just from a simple image. There's a couple ways to do that. The first one, people are probably most familiar with, splitting the white light that we see from most things apart with a prism into its colors. There's lots of diagrams of this. Personally, I'm partial to the Pink Floyd variation on the top there. But you're familiar with seeing this now in your day-to-day life, especially if you happen to be fortunate enough to go to a place like Hawaii where it rains a lot. When you see a rainbow, either after a thunderstorm or near a waterfall, then you're seeing light being dispersed into its colors with a prism. The prism in this case is water droplets in the air. The white light shines into the water droplets. The different colors of light refract slightly different amounts. They start to bend away from one another. Then it bounces off the back, comes straight back towards you. And the colors of light are now split. So instead of seeing white light, you're seeing the red and blue light at different locations in this rainbow that you're seeing. And it gives you this lovely traditional rainbow type shape. There's another way to do it though, and that's using something called a grating. So a grating is a piece of hardware. It's usually pretty small, about yay big or something like that, which we've drawn lines on, very closely spaced together. It looks like kind of a set of steps like this. And that works somewhat in the same way as well. When light hits that, those steps are close enough together that light of different colors interferes with itself and also makes it split apart into these different colors, blue through red. And it's a lot easier to control with this exactly how much splitting you get of the colors. Depending on how closely you draw the lines together and exactly what angles you use, then you can get either very large splitting or very small splitting of light, depending on what science it is that you want to do. You're actually familiar with this kind of way of diffracting light into its colors as well. Next time you pick up a CD and you look at that sort of shimmer of colors on the bottom of it, you're seeing light coming off of a grating like this. All those little tracks grooved into the CD act like a diffraction grating and split light into a rainbow, just like it is we're used to seeing with these kinds of gratings. So really, those two things, the prism and the grating, are the heart of any spectrograph, whether or not it's something that we're using in our own backyard or if it's something really fancy that we put up in space. This is what a typical astronomical spectrometer looks like in rough diagram form. The heart of it is this piece here, in this case a diffraction grating. There's a bunch of fancy optics up here. Maybe that's the 2-inch telescope you've got at home. Maybe it's a $10 billion space telescope. But either way, it's acting as a really big light bucket to focus the light from the object that you're looking at down into one place. You bounce it off of that diffraction grating, split it into its colors, bounce it again into a camera, whether or not that camera is your eye or a photographic plate or an electronic detector like you've got in your digital camera. The answer is essentially the same. You record that image and look at that spectrum that you've recorded, and you can see the light from your object split out into all of its different colors. One of the first people to do that, with a very small telescope, obviously, back in the 1700s and 1800s, was Joseph Fraunhofer, who used this kind of an instrument to look at a number of different sources, matches, candles, the sun. And one of the fascinating things that he noticed when he pointed this instrument of his at the sun was that he got a spectrum that looked something like this, in the sense that he didn't just get a rainbow of blue through red. It was pretty much a rainbow, but there were these weird dark lines in the spectrum. And he didn't really know what to make of these, but they were certainly there. They were very noticeable. They were identifiable, and he took to giving them names and numbers to indicate which of the lines in the spectrum it was. But what we now know is that those lines are the fingerprints of the elements that we see in the universe around us. I can jump forward a couple hundred years or so in time and show you a modern version of that spectrum. This is now a much higher resolution spectrum of the sun taken by the National Optical Astronomy Observatory. And you're seeing the traditional expected rainbow, so red up on the top to blue down the bottom, but you're seeing all of these dark lines scattered throughout. And the different kinds of lines as well. Some of them are very faint, some of them are dark, some of them are skinny, some of them are very wide. And what all of these are telling you something about the composition of the sun. They're telling you about the elements that are within it, how those elements are moving, and what the pressure of the gas on the surface of the sun is doing. So while this is really pretty, it's not a very useful way to try actually doing science with it, though, because I can't point to this one and say, yeah, that one next to the thinner one that looks like it's slightly not quite as dark. It's hard to really do anything quantitative that way, so I'm going to change the format I'm showing these spectra to you in a little bit. I'm going to go from this up top to this kind of a display on the bottom. This is just a graphical representation of the spectrum that you're seeing up top. We're now, instead of just attempting to do color shading to indicate how much light you're getting at a specific wavelength, I'm showing you that in terms of the intensity field here. So where you get that dark line here, I suppose I could use the laser pointer, but I just walk too much anyway. That dark line here corresponds to that dip in the spectrum down here. Similarly, the dark line over there corresponds to these little dips. You can see that they're much shallower. They're dips in the spectrum, but they don't go as deep. And when we manage to plot the data in this kind of a form, it's a lot easier to actually do science with it and say, no, the line at 433.2 nanometers that goes halfway down the spectrum. It's a lot easier than looking at the top plot, although I acknowledge it is a whole lot less pretty. So we get spectra like this when we're looking at typical astronomical objects. This is a spectrum of a galaxy in this case. This one is probably an early type galaxy, not much ongoing star formation looking at it. But you can see the kinds of complexity that you get when you're looking at sources beyond stars. You've got a bunch of very deep features, a bunch of tiny features, some features are slightly broader, even broader features there. And the vast majority of what you're seeing in there isn't just noise, it's actually signal. There's lots of little features telling you things about the object that you're looking at. So I'll break up what we can learn from spectra like this into sort of three main classes and tell you a little bit about each of those. We can look at what lines are present in there, and that can tell us what the composition is of the object we're looking at. What kinds of elements are in it? Does it have hydrogen in it? Does it have iron in it? Does it have calcium? How much? Where is it? How hot is it? How dense is the gas that's producing it? Is there much in the way of a magnetic field in there? Those are all kinds of things that we can tell just by looking at which lines are there. Based on where the lines fall, if they're here or a little bit that way or a little bit that way, it can tell us about the kinematics. Is this gas moving towards us or away from us? How fast is it moving towards or away from us? Those kinds of things we can use as ultimately the evidence for dark matter and our understanding of the expanding universe. It comes from spectra. You can look at the line width and the line strength. How deep is it? Is it just a shallow little line? Is it a really deep line that goes all the way down to black at the bottom? Is it really wide? Is it really narrow? That can tell you about the range of velocities in an object. Are you looking at something that's, say, a black hole with an accretion disk with stuff spiraling around it super fast and making a very broad line? Or is it really narrow? Is it a star that's got a very large radius or a small radius? That changes the surface gravity of the star and how wide those lines are. There's an incredible wealth of information that we can get out of these kinds of spectra. And I'll show you a couple examples of those now. Here's the cluster that I showed you a couple slides ago with those blue and red stars. And on the right is me trying to make good on the waving hands that I was doing earlier and saying, how do we know that they're hot versus cool? On the top is an O-type star. It's one of these hot stars. This is what its typical spectrum looks like. Where now I've still got that wavelength plot down the bottom from blue all the way out to red. You can see it here, the extremely inventively named B for blue and R for red filters. V is green for reasons that I won't go into, and it gets really weird when you get into the infrared. Quite possibly it looks like you are nodding your head, probably coming from the French. And you get into the infrared, it goes into J, H, K, and all sorts of other strange things. But when you're looking at a hot star, one of these so-called O stars, you can see how much more light it has in the blue up here than it does in the red. Because it's got so much more light in the blue, it appears blue when you take just a photograph of it with HST. Similarly for these old kinds of stars, the so-called M-dwarf stars, they have a lot more light in the red than in the blue. They appear red in these kinds of figures. The Sun, for comparison, is one of these kinds of stars, a G-type star. It's pretty much flat across all of them, so it looks kind of whitish or yellowish when you actually look at it in terms of color. So I could spend a good chunk of time talking about how you actually classify stars according to all these different kinds of features that you see within them. Happily, I don't have to, because that's the talk you guys are going to be treated to next month. There's going to be an entire talk on the classification of stellar spectra that I'm actually looking forward to seeing as well. So I'm going to gloss over that for now and sweep it under the rug, and just talk about what we can do with one of these kinds of stars. We'll focus on this one. We'll take a star. So it's a little bit hotter than the Sun, but not the hottest kinds of stars that we can get. And let's see if we can understand, why does it look like this? Why does its spectrum have that shape? There's two components to it. There's the broad component here, the overall shape of the spectrum, how it rises, peaks, and then declines as you go to the red. And then there's these absorption features in it. And we'll take each of those separately. Here's the broad component. It's something called the Planck function, which what it essentially is that any dense, hot objects in the universe give off light. They radiate with some kind of a characteristic spectrum that's described by this kind of a shape. And it shifts back and forth depending on exactly how hot the object is that you're looking at. If you're a hotter object, it shifts further to the blue. The light is more intense, more energetic. It looks bluer than it does for cooler things. So those hot stars, the so-called O stars, peak around here in the blue, tail off in the red, and get fainter in the infrared. The M-type stars, the cooler stars, they actually peak here in the infrared and have very little in the blue. Everything does give off this kind of radiation. If you look at yourself in the infrared, you're giving off light right now as well. We can't see it because we can't see infrared radiation with our own eyes. But I could include a person or anything at room temperature on Earth on this plot as well. In comparison, it would be teeny, teeny tiny and way down here in the infrared. But you can make this plot for really anything that has temperature. It's just hot stars that really make something that we're interested in for the present moment. So that gives us our continuum. What is it that gives us our lines imprinted on top of it? Here's the continuum, here's the lines. It turns out that for A stars, it's actually really simple to understand what lines you see in their spectra. If I take observations on Earth of the element hydrogen, and I take it into a lab, I make it glow, I take a spectrum of it, looks about like that. You get a characteristic line in the red, about 65, 63 angstroms, another one in the blue, some more in the further blue, and oh look, they line up exactly with the wavelengths that you're seeing in that star. This is how we understand what elements there are in the atmospheres of stars and how hot those atmospheres are. We can see, looking at this, that it is hydrogen that we're seeing in the atmosphere of this star. Not just is it hydrogen, it has to be the right temperature and density of hydrogen in order to give us this kind of characteristic radiation. To understand that, I'm going to need to take a momentary sidestep into a little bit of physics. I promise to return to astronomy in a minute, but the main benefit of spectroscopy is it allows us to put the physics in astrophysics. Here's a schematic diagram of the atom. We'll keep it simple. We'll work with hydrogen, one proton, one electron. Let's not mess with any of the more complicated stuff right now. That atom doesn't have a full range of energies that you can give it. You can't give the electron in that atom any energy at once. It has to sit in a couple different specific energy levels. You can think of it like little rings it's orbiting the proton on. There's a little ring down here at the bottom. Let's call that the first ring. A second ring, a third ring, a fourth ring, going further and further out. And each of these rings, an electron sitting on that, has a characteristic energy. When you walk up to that atom, and you kick it, or you shine light on it, or something like that, you make that electron jump between those different rings. And depending on which rings it jumps between, that's a very specific energy it takes to do that jump. That very specific energy corresponds to a very specific wavelength and hence a very specific color. So when we see things like this in the hydrogen spectrum, this red line here is this red jump right there between the third and the second ring of hydrogen. If we were to jump between the fourth and the second ring, it would give us a different line, and so on going on out. There's a whole series of these different lines you get between different rings. These are all in the visible. There's similar jumps here that happen in the ultraviolet that we can't see, and out here in the infrared as well. But that's why you get that characteristic fingerprint of different wavelengths of emission from different elements that you're looking at. It gets really complicated really fast when you look at things other than hydrogen, so we'll just stick with hydrogen for right now since it illustrates the idea. You can probably see, though, that sometimes you've got it in emission and sometimes in absorption. Sometimes I've got these bright lines, and sometimes they're just these dark lines in the background. The reason why is that tells us what it is you're looking at in terms of how it's lit up. So if you're looking at a background thing like a star, let's say the star is just deep within the star. It's not technically solid, but it's so dense that it may as well be solid for the sake of producing a continuum radiation. That's lighting you up. If you could look straight at that without any atmosphere surrounding it, you would get a nice rainbow spectrum with no lines in it whatsoever, just from blue to red, out into the infrared and out into the ultraviolet as well. When that light shines through a cloud of gas or an atmosphere surrounding the star itself, that gas, whatever's in it, lights up. Most of the photons go flying straight through, but any of them that are able to kick electrons between those different rings get stopped really fast. Most of that red light goes through, but red light that is right here in frequency runs into an atom, kicks an electron up, gets stopped, gets shined out again in a different direction, gets stopped, gets shined out again in a different direction, and scattered all over the place. What that means is that light at those wavelengths really just doesn't make it through that cloud really well. It keeps on getting pulled over and stopped and redirected off in different directions. So you don't see as much of that light out the other side. That's what gives these black features. If you're looking sideways into it, I was about to point with a laser pointer before I realized that really wouldn't work terribly well. If you're looking upwards into it like this, you only see the light that's been redirected, the light that keeps on getting pulled over and stopped and restarted again in different directions. You don't see the continuum because that's just trucked straight on through the cloud without stopping. This is what you see instead, those bright lines at those characteristic wavelengths. So what you see is telling you about the gas that you're looking at, whether or not it's lit up from behind, whether or not it's lit up from the side, and what the qualities of that gas are in terms of its temperature, its density. That tells you what kinds of lines you're getting from all the various different elements. As I told you, it gets complicated really fast. Here is the spectra of each of the elements, modulo some down bottom that don't look like they've got much in the way of data. Hydrogen up top has that characteristic bright red line, about 65, 63 angstroms. That's one of the most important lines for the study of many things in astronomy because it's very bright and we can see it for great distances. Oxygen has another very important line. It's in the green. That's something else we use important for the study of galaxies. Sodium has a bright line in the yellow, and that's very important for studies from the ground. If we use adaptive optics, laser guide stars, all that you might have heard about, often using sodium because it's got a nice contained bright yellow line you can look at that isn't so wide that it'll muck up a lot of your observations. All the elements have various different fingerprints, and you can learn about what's in an object by which of those lines you see in your target. It's not just restricted to atoms. You can get even more complicated and say molecules. Molecules have these kinds of fingerprints as well. So if you look in, say, the moon, Titan, you can take a spectrum of that and see that there's this feature in the spectrum that corresponds to CH4, also known as methane gas. So that's how when we tell you that we see methane in the atmosphere of Titan, that's why. We can look at the spectrum and say the only thing we know of to produce that characteristic signature is methane molecule. That's how we know what's in not only Titan, but also in other planets as well. There's another couple lines in there you see as well. There's a hydrogen line from the sun, and there's an oxygen line there too, marked as Earth. And that's a reminder to us that these dark bands we get in our spectrum will happily be imprinted by anything the light travels through, whether you want it to or not. That actually becomes really difficult, really fast when you're observing from the ground. This is what the typical night sky looks like from a fairly dark site out in New Mexico that we took over the last couple of years or so. You can see as excuse me, you get out to the infrared, you get just this hairy forest of oxygen and water lines that they're really bright and they're emitting straight into your telescope, which makes it very hard to actually do much in the way of infrared astronomy from the ground because you're fighting with all of that water vapor happily radiating away straight into your telescope and blocking or overwhelming the light from the signal from the galaxy that you're trying to study. Even in the blue, you got fun features as well, not only sky lines, but also, in this case, mercury and high-pressure sodium lines. That's street lamps coming from the towns around Apache Point. It shines out of the towns, bounces off of the atmosphere, and we then record it in our data and have to calibrate it out very carefully. It's a reminder to us, though, that it's always worth considering things closer to home when we're trying to understand what we see in spectra. So there's a fun story to do with potassium flare stars. I told you about how people have been trying to study the elements in stars for a long time. Earlier in the 1900s, then, there were a number of observations of some kinds of stars where they noticed that these stars occasionally had flares of potassium that showed up in them and then disappeared again in the next exposure. And they're very irregular. Sometimes they were there, sometimes they won't. Nobody seemed to be able to reproduce the observations. But just as soon as they thought that they'd gone away, some of them would come back again. And a lot of people were scratching their heads trying to figure out what it was they were seeing. And the problem seems to date back to this interesting passage that I found in a scientific proceedings from the late 1800s or so, describing a new kind of spectrograph, a so-called Coude spectrograph. It's essentially a fancy name, loosely speaking, for a special room in the observatory where you can put your spectrograph. Now, instead of having your spectrograph out on the telescope, because it gets cold out there at night, and you're out there all night, you don't really want to do that. Just shine the light from your telescope into a special room. Here's a cutaway of the Palomar 200-inch telescope. This special room, called the Coude room, is where you could install your spectrograph, send the light in there, keep it warm so you can be comfortable, sit down in your chair, smoke your pipe if you wish, and therein is the problem. After quite some investigation, it was found that the light baffling in a few telescopes' Coude rooms was not actually ideal, and occasionally when the observer went in there, well, I suppose they didn't have lighters, they wouldn't have lit up. When they struck a match to light up their pipe, the potassium in the match flared and got recorded on the spectrograph. So potassium flare stars actually work out to be a lot closer to home. They are matches instead. But it's an interesting example of you have to have good control of your systematics, and anything will happily imprint upon your spectrum. The trick is deciding exactly how far away that thing is. So let's change topics a little bit and talk about spectral line shifts, what we learned from that. So just like the Doppler shift affects sound that you hear, the Doppler shift affects light as well. If an object's moving away from you, it shifts those lines and moves them a little bit to the red. If it's moving towards you, it moves them a little bit towards the blue. In case you thought it wasn't hard enough to identify them when they weren't moving around, now we're going to move them all around freely as well. It's a trick to identify them when they jump around. So if you've got a typical galaxy spectrum like this, here's the non-star forming spectrum, here's a star forming type spectrum with emission. You want to measure that for a galaxy and say, where are those lines and how do they shift around little bits depending on what part of the galaxy you're looking at. And that can tell you about how the galaxy is rotating. When that was done, we found something really curious. Now, go back in the mid to late 1900s or so. Here's a plot looking at the effect of rotation velocity as a function of radius in this galaxy, in this case M33. What we found is that instead of now the rotation velocity, so how fast stars in the galaxy have to go to keep going around on circular orbits around the galaxy, we would expect that it increased for a little while, stayed kind of flat, and then decreased. Because the light in the galaxy is centrally concentrated, as you go further out, there's less light, therefore there's less stuff, so you shouldn't have to go as fast to keep going in a circle. What we found when looking at velocities from these spectra, though, was that that wasn't what happened. The velocities kept going up, and that was really bizarre. You would expect that if they kept going up like that, they would just fly straight out into space and not stay in the galaxy at all. There wasn't enough stuff in the galaxy to keep them bound if they were going that fast. We can put together light from stars and similar kinds of measurements, looking at hydrogen emission but at radio wavelengths instead of in the optical. And this difference here, we can paint dark matter in there. That's the evidence for dark matter when we see it in nearby galaxies, that difference. It's telling us that there's some extra stuff in the galaxy that we can't see, but whatever it is, even though it doesn't give off light, it is whipping those stars around faster than they otherwise have any right to be going. But that's the origin of the dark matter story, is that difference there that we observed from spectroscopy.
Is there with that diagram you have there, evidence for dark matter expected from visible disk and then the 21 centimeter hydrogen? Does that give you a better answer about the dark matter?
I'm not sure I understand the question.
Pardon?
I'm not sure I understand the question.
Well, they keep talking about dark matter, that they can't put their hands on it. Can't see it, all that. You've got an expected graph for visible disk.
Ah, yes, okay.
Down you have one for your hydrogen. Now you have a parameter, high-low, which gives you plus and minus for what would be.
Right, is it just regular gas that you just can't see because it's not in the form of stars?
It's limiting it into a smaller box.
Right, so there's always the question of, is it just regular mass that's out there, but you just aren't seeing it because it's not shining for whatever reason? And it would have to be such an enormous quantity out there that's just incompatible with what we understand about galaxies and how much hydrogen can be out there. We can use other traces as well. We can look at other galaxies orbiting around this one and see from how fast they're moving. There's really just so much out there that it just simply cannot be all hydrogen gas or something that's just too dark to see. It has to be something that is genuinely not radiating at all, something that isn't interacting electromagnetically, but gravity says that it has to be there. So anyway, while I'm happy to talk about dark matter, in fact, I'd be happy to give an entire talk on it at some point in time, we probably don't have time to dwell on it right now. At the moment, it's more of an interesting, this is one of the important things that we've learned from spectroscopy, and move on to something else. So,
The faster an object is moving, the larger the shift is.
if you go to a nearby star, it's a little shift. A nearby galaxy is a bigger shift. A distant galaxy is an even bigger shift than a very distant galaxy. Well, now we're taking light that used to be blue and making it green, or even worse, making it red if you move too far. That led to the interesting observation in the early 1900s from Edwin Hubble that if you made a plot of how far away galaxies were, because near enough galaxies you can work out their distances through a variety of techniques. If you plotted that against their velocity, you found that the further away galaxies were, the faster and faster and faster they were moving. This is the origin of our current understanding of the expanding universe. In order to understand this, it doesn't make sense to think that there's something about the galaxies themselves that are making them move that fast. More, it's a property of the space in between. The space in between is expanding, so the more of that space you have, the faster and faster away things are moving. So this was made from looking at velocities, our understanding of the expanding universe. You can continue this further in a variety of other ways, but that's the origin of the expanding universe theory, looking at radial velocities and how they get faster with distance. That's also now how we know how far away galaxies are when we look at fields like this. This is the Hubble Ultra Deep Field. Probably many of you have seen it before. Almost everything in here is a galaxy. I can pick out the stars, and there's a star, etc. Most of the stuff in here is galaxies, though. And some of the really teeny tiny faint fuzzy ones in there are the kind of things that I study. And we know how far away those are when I tell you that's at redshift 3. What that means is that we've looked at the spectrum of that object, and we see that instead of the light that's meant to be in the green, coming out in green, we actually observe that in the infrared instead. It has shifted so far, the red shift is so large that it tells us it's a humongous fraction of the age of the universe, or the distance of the universe away from us. So we might have a spectrum like this, where some of the spectra that we got like this in early days that we looked at, a lot of people puzzled their heads over them and wondered for a long time what they were, because the lines didn't seem to look like anything familiar. They didn't look like hydrogen, didn't look like helium, didn't look like carbon. So there was a theory for a while that some galaxies just had this weird element called nebulium in them, which didn't correspond to anything on Earth, but we saw it in some galaxies. Turns out it's not nebulium or anything that weird at all. It's just the regular elements that we're familiar with, but shifted so far that we're looking at a completely different part of the spectrum. Now, what we're looking at in green is these lines that are usually hanging out about a factor of 5 or so less in terms of their wavelength, in the far ultraviolet instead. And it took a while to identify this, but once we learned that, it became a very powerful tool for studying galaxies that are extraordinarily far away. In this case, about 11 billion or so light years back in time. So in this case, it's a combination of different things. This is oxygen, carbon, and silicon lines. In this case, we're seeing absorption in the middle of interstellar medium of these galaxies.
So there's another question. So if you're looking at absorption lines, how do you know that it's an absorption of the something closer to you? Doesn't the light from far away places go to clouds that are intervening?
Yeah, and that's actually a fantastic way to learn about stuff that's along the line of sight. So in galaxies like this, then most of the absorption actually happens in the galaxy itself. So the lines all line up in the right place to be those elements in that galaxy. But one of the really cool ways we have of studying stuff in the universe that doesn't radiate, the gas that doesn't give off much light of its own, is by looking at bright beacons, if you will, in the distant universe. Pick something super bright and super far away, a quasar, for instance, out at redshift 3, and we can look in its spectrum and see absorption from hydrogen all the way from redshift of 3 down to today, and use that to learn about where the hydrogen is along that column.
So basically, there's not enough clouds in between. There's darkness between the various things that you're looking at. And every once in a while, you see a cloud of gas in between.
To a degree, although there's actually some cool science you can do where things go what's called optically thick, and you get so many lines all stacking up on top of one another that your spectrum just goes black and goes to 0, which happens if you go sufficiently short in wavelength, where because everything is shifted, then at some redshift or another, every wavelength from the galaxy shortwards of a certain limit is going to be just right to be absorbed by hydrogen. And then you can sometimes get just a black spectrum with no information at all. And that is one way that's used to study galaxies in the very distant universe, select those galaxies, and learn about the hydrogen in between the two. So that's a sort of very quick tour of some of the things that we can do with spectra and why spectra are cool. They teach us a lot of what we know about the universe. They teach us what things are made of, how hot they are, how they're moving. But it's still kind of limited in some ways, in the sense that traditional spectroscopy, like I've talked about, has studied millions and millions of objects. Surveys like the Sloan Digital Sky Survey have taken spectra of millions of galaxies, and it takes a galaxy like this, it puts a fiber in the middle of the galaxy where you want to get your spectrum. If you're really lucky, you might not be using just a fiber, you might be using a slit instead, so you get a spectrum along some big narrow line like that. And from that region, you get everything you know about the star in terms of its star formation rate, how rapidly it's forming stars based on how much hydrogen emission you're seeing, what its metallicity is, how much carbon, iron, etc. you've got, whether or not there's a black hole in the middle of it and how active that is, how it's moving, how the stars are rotating in the galaxy, how massive the galaxy is. But there's a lot of the galaxy that we're really missing in doing that. What you'd really like is that instead. And the middle of the galaxy is great, don't get me wrong, but it's biased. If I'm looking in the very middle of the galaxy, it doesn't tell me anything about what's happening out here in the disk, or out here in the halo. The halo is really important. That's how gas gets into and out of galaxies. That's how things cycle and keep galaxies alive, and how galaxies die, getting gas from and losing gas to their environment. You just don't get a lot of that in traditional spectra, so this is what we want to do. This is the idea behind integral field spectroscopy, or three-dimensional spectroscopy, where now instead of just getting a one-dimensional line of sight straight through that middle, you've got 3 dimensions instead. You've got 2 dimensions on the sky, and 1 dimension of wavelength going down through your object. So there's a couple different ways to do it, but this is the rough set of ideas. Now you have some object on the sky, you need to chop it up into different pieces. You can either do that with little fibers, little circles like I showed you on the previous picture. You can do it with lenslets or little squares to keep with a little circles theme. Or you can do it with lots of little slits like this, all spaced close to one another. You get spectra of each of those, image them on the detector, and then you stack them together into these data cubes. It looks something like this, to show you an example from one of the surveys that I'm involved with, where here you're looking at the image on the sky. In this case, I'm moving a star or something like that around in the field of view of my fibers. You can see depending on where it lands, it lights up different fibers, depending on how much light lies behind those fibers. You get something like this on your digital camera when you take a picture. Here's all those little different fibers that I'm lighting up. So maybe this one's close to the middle of a galaxy, it's bright. Maybe this one's in the edge of a galaxy, it's faint. And this is the wavelength running up this way. This is probably something in the atmosphere, one of those water emission lines. So you can take all of these little spectra and rearrange them, because looking at that really doesn't tell you very much easily. At least I can't look at that and tell you, oh yeah, that's a galaxy spectrum. You have to rearrange it in order to get anything useful out of it. But when you do that, it gives you something that looks like this, where now on the left I'm showing you a Sloan color image of a galaxy, and on the right I'm showing you our IFU spectroscopy of that galaxy. It's not quite the same resolution, but now instead of a pixel being a pixel, you can say, oh, it's yellow. What is yellow? Now I can tell you that yellow bit in the center has a spectrum that looks like that. It's got strong hydrogen emission. It's got strong oxygen emission. It's probably forming stars fairly rapidly. I can tell you about where the velocity is from the shifts of all of those lines. And I can do the same thing out here on the edge of the galaxy as well. I can tell you in that tidal tail, no, the emission lines aren't quite as strong. Maybe it's not forming stars quite as fast. Maybe it's moving towards us a little bit more than the elements in the middle were. I can make maps now of the velocity of the galaxy. Instead of just saying, I think it's plus minus 200, I can say, this is what the velocity looks like. Here's what the stars are doing, and here's what the gas is doing. In this case, down the bottom, there's this really neat arrangement of 2 galaxies in SDSS. We've got 2 galaxies that look almost like they're colliding. I can make a map of the hydrogen emission and say, the star formation in the big one makes this big ring that looks like the smaller one's about to go right through the middle of it. Probably isn't, but it looks that way on the sky at least. And I can map what the velocity is doing. Here's the red-shifted part of the big galaxy and the blue-shifted part. The red-shifted part of the little one and the blue-shifted part of the little one. It really gives you an entirely different dimension of power on understanding what's happening in galaxies when you don't treat them as point sources in this way. So they're becoming a pretty powerful new tool for current telescopes. There's a number of IFUs on the VLT down south in Chile. There's a couple out on the Keck telescopes in Hawaii. There's Sirius Spectrograph, the Keck Cosmic Web Imager that's coming online. I'm really excited, actually. It's coming online later this year, and we just put in a proposal to use it to do some cool stuff. And big survey telescopes, like the Sloan Digital Sky Survey. The MANGA survey is now getting into surveys of large numbers of galaxies, and a number of other surveys that have come before as well. So this is one of the projects that I'm involved in, the Sloan Digital Sky Survey, targeting 10,000 galaxies with this kind of integral field spectroscopy. Here's kind of a close-up of how we're actually doing that. I showed you diagrammatic pictures before of all those little circular fibers next to one another. Here's what it actually looks like when you build the thing. It's about that big. It's pretty tiny, actually, if you hold it in your hand. And you can take it and plug it into plates like this one, which you're welcome to come up and look at later. This is one of our plates from early in the survey, which has lots of little holes in it. If I could get it backlit, there you go, maybe you can see the backlighting a little bit. All those little dots in there telling you about where the galaxies are that you want to study. Same idea behind the original Sloan, but now in 3 dimensions instead of 1. And that can tell us a lot of interesting things about galaxies that we hadn't learned before. To give you an example of a couple of them, one of the things that the Atlas 3D survey, which is one of the very first IFU surveys, learned when it looked at elliptical galaxies is that they actually aren't such boring things as they're often given credit for. Elliptical galaxies are often regarded as the red, the dead, the just kind of dispersion-dominated things that aren't terribly interesting and aren't forming too many stars. They found that that's really not true at all. A lot of the elliptical galaxies are actually rotating reasonably fast, just like spiral galaxies, which is forcing us to rethink our understanding of the Hubble sequence. Instead of just a sequence between spiral galaxies, which form stars and rotate, and elliptical galaxies, which don't form stars and don't rotate, instead we can think of it more in terms of a sequence of rotation versus gas content, where if you are slowly rotating, you're probably a standard elliptical galaxy. You're not forming very many stars, and you're not rotating. If you are rotating and you have gas, you're spiral. If you don't have gas, you're elliptical or lenticular, more accurately. But there's a gradient all between the two, and it recasts the Hubble sequence not as a tuning fork, say, but perhaps more physically as a comb instead, a sequence in some physical measurables for the galaxy, like how much it's rotating, how recently it interacted, and how much gas is in it so that it can form stars or not. We can learn other things. We can take those various different lines, how strong are the lines of hydrogen, oxygen, nitrogen, etc., and we can make ratios from them and say, well, based on how strong the hydrogen is to the oxygen line, then we can say what mechanism is heating that gas. Is it being heated by stars? Is it by heating by a black hole? Is it being heated by a whole lot of pressure just ramming its way through the galaxy and exciting everything as it goes? And we can make that also into maps for galaxies. So we can say for, this case down here, this blue region out here is stuff where the ratios of the lines is consistent with being lit up by star formation. In the middle, it's consistent with being lit up by older stars or with active nuclei, and use that to learn about where the star formation is really happening in galaxies and what's turning it on and off. We can learn other things as well. This is a case from one of the papers that we published a year or so ago, looking at some galaxies which were cutely named Akira and Tetsuo for the popular culture reference. Akira is a elliptical type galaxy which shouldn't have much in the way of ongoing star formation and doesn't. But when we look at it with an IFU, we actually see hydrogen emission in it. What we think it's telling us in this case is that it's hydrogen emission blowing out gas that would otherwise be forming stars, but the AGN in the middle of the galaxy is putting a brake on. It's putting a screeching halt on the accretion of gas, saying, nope, nope, we don't want you here, blowing it back out into the surrounding environment before it can form stars, and helping confirm the theoretical idea, at least, that very massive galaxies really can't form stars once they get too big. We're seeing that in action here, where it tries to get gas and just can't hold on to it. To take a step out into the more distant universe quickly, there's this galaxy with another fun name, like the one that we talked about in the beginning of this session. This one's Q2343BX442. My wife still gives me a hard time over this name and says I should have named it after her instead, which in retrospect perhaps I should have done. But at the time it was just one more catalog object in our survey. What we found when we looked at it with HST is that it looks like a spiral galaxy, except this thing is so far away from its spectrum, we can identify all of these features. It tells us that it's about a redshift of 2, or 10.5 billion light years away. our understanding of galaxies that far away in the universe is that there should not be spiral galaxies there. So what's this one doing there? Is it just that, the argument I got from a lot of people when we first found it was, it's not really a spiral, it's just a lot of pieces that kind of look like they're a spiral. If you look at enough galaxies, you get things that look like whatever you will. Like one of my favorite galaxies looks like the Mitsubishi sign. Unfortunately, we can't follow up on that, but James Webb. So we want to follow this up with an IFU, because then we can say not just it looks like a spiral, but we can say, is it moving like a spiral, and what does it tell us? So we looked at it with the OSIRIS IFU a few years ago now, spent 13 hours or so just staring at this one spot for many nights. And what we found was this. Here's what the hydrogen mission looks like from it. You can see that kind of spiral structure still. Here's the actual IFU data itself that I made a movie out of. What we're doing here, this is the same location on the sky, X and Y, but the movie is stepping through in wavelength. So you can think of it stepping through in velocity. So blue, less blue, middle, red, more red, as you go through in time. So you're seeing this gradient from blue to red across the galaxy. That's telling you that the galaxy itself is rotating. It's a little hard to get too much information out of the movie, although it shows you kind of what the data looks like. If I actually put that in terms of velocity maps, I can show you this. And I can say, here's what we observe the rotation. This side is red shifted, this side is blue shifted. And here's what you'd get for a model if it was a rotating galaxy. They match very closely. Not only does it look like a spiral galaxy, it's moving like a spiral galaxy as well. Not only that, though, it's hot. The individual parts in the galaxy aren't nice and cold like galaxies in the nearby universe, or disk galaxies in the nearby universe. They have heat of maybe 10 kilometers a second. What that means is that the disks are thin. Stuff doesn't go really high out of the disks before it comes back down again. This one's really hot, more like 70 kilometers a second, and like the other galaxies we see at that redshift. So what it's telling us is that we can form galaxies that look like what we know today, even in the very hot conditions that were prevalent in the early days of the universe in terms of galaxy formation out at about a redshift of 2 or so. And that's something that's really tied fundamentally to the integral field approach in order to get that observation. You need spectroscopy in order to find what the state of galaxies is and why they behave the way they do. So that was a quick tour on some of the cool things IFUs have done, but it's probably worth closing with a quick tour of some of the cool things that they will do in the next generation. These techniques are becoming standard on next-gen facilities as well. Big telescopes on the ground, like the 30-meter telescope, the Giant Magellan telescope, and others, will have these kinds of instruments as the standard instrument suite from the very early days of the telescope. James Webb will have 2 of these IFUs on the MIRI and NIRSPEC instruments. And the WFIRST telescope is slated to have a integral field unit as part of it as well, with the aim of studying supernovae in the very distant universe and learning more about the expanding and accelerating universe. James Webb in particular is going to put the first of these near and mid-infrared IFUs in space. And when I say in space, I mean really in space, all the way out at L2. None of this low Earth orbit stuff, but way out in space where you have to get everything right the first time. So as part of my work here, working on James Webb, getting that right the first time is what takes a large amount of my day job trying to make happen for these integral field units. What that's going to do is really allow us to do stuff that is unthinkable currently from the ground. So I showed you that plot a while back about what the Earth's atmosphere looks like, how bright it is in the infrared. Turns out it gets even worse the further you go into the infrared. Here's a plot of how much the atmosphere transmits light as you go out into the mid-infrared. There's kind of some areas where you can do okay, out to about 2 microns or so, but by the time you get out to 6 microns, 14 microns, and longwards, really you just don't get anything through the atmosphere. And what you do get through has this gigantic flashlight of the atmosphere itself glowing. I mentioned that everything that's dense enough glows. Well, the atmosphere glows, and unfortunately it glows really brightly in these wavelengths. That means it's almost impossible to see anything that's particularly faint when we're looking in the mid-infrared from the ground. In contrast, if this is the background on the ground from the very best dark sky sites, this is the background we're expecting to get with JWST. So it's what, 6-ish orders of magnitude, 1 million times lower background. And that's going to really open up this wavelength range for the very first time with such an instrument at such a large spectral resolution as these instruments are going to be able to get to study. And it's really exciting to contemplate some of the things that'll let us do. Near-spec and MIRI are both of these slicer-type spectrographs. So it slices up the light in this kind of format. It gives us something that looks like this for our objects. We get spectra from each of those pieces and put them back together into something that's a little bit more sensible in a cube-type format. And it'll allow us to do things like this. I'll start close to home and end my talk out in the very distant universe. Close to home, it'll let us look at things in the solar system. Uranus and Neptune, so they actually really nicely fill the sizes of these IFUs on the sky. No more just looking at a single point on it or a single slit across it. Let's just get the entire thing. Let's learn about the weather on Uranus, the weather on Neptune, the weather on Mars, Titan, whatever it is you want to look at. Out at these wavelengths, we'll get all these various different features from complex molecules in the atmosphere to tell us about what the atmosphere of these planets are and how they're structured. You can step out a little bit further and say, now let's look at young stars nearby, forming stars near the solar neighborhood or in bright regions in Orion, where you're seeing young stars forming for the very first time, still perhaps embedded in the disks that are going to go on to become planets around these stars. You can look at those and say, I see water ice, I see methanol ice, I see methane, I see other kinds of ices in the spectrum as well, which is going to tell me about how these stars are forming and how the disks of debris around them are forming as well, and whether or not they might be on track to form something like our own solar system or something completely different. And this is opening wavelengths that are just completely inaccessible now through similar techniques. I can look at galaxies in the nearby universe. I can study the black holes at the middle of them. These kinds of wavelengths will have a number of sort of exotic lines from things like 5 or 6 times ionized neon, argon, other kinds of exotic things that tell us a lot about what the detailed structure is of that black hole region and how it's exciting the galaxy around it, which could help us learn about what the relation between black holes and their host galaxies is, both in galaxies near us and going out into the further universe. And taking another final step, going to very high redshift galaxies. Now, there's galaxies like this one, which I showed you, which was neat, but it was just one galaxy. And we had to spend 13 hours with one of the biggest telescopes in the world looking at it. James Webb can do this in an hour, possibly less. But that's not really what makes it exciting. What makes it exciting is that we can do fainter objects, we can do further objects, we can do more interesting things that are just completely beyond reach now. We can push from redshift 2 out to redshifts of 5, 6, 8, all the way up to first light, and hopefully detect some of the signatures of light from some of the very first sources of radiation in the universe. That's some of the exciting stuff that we're hoping to get out of JWST, using instruments like these and similar instruments in the coming years. So I'll wrap up and say James Webb is coming soon. Launch is in fall of next year. There's a lot of work currently ongoing to get ready, but we're really excited, looking forward to turning James Webb from this kind of a dream into a reality and giving talks on the science we got out of it. Thanks. Okay, there's probably some time for questions at least, right?
Yes, we have some time for questions. All right, do we have any questions? Yes.
Yes, earlier in the talk, you mentioned spectroscopy was used to determine composition of galaxies and also infer the presence of dark matter. So in kinematics, now you weren't suggesting that any of these spectrographic techniques were used to determine the composition of dark matter, were you?
No.
All right, so the question was, has spectroscopic techniques been able to determine the composition of dark matter?
No, techniques like I was talking about there simply allow us to infer the presence of dark matter by understanding how things move. There's other ways that are much more exotic that you can try and understand potentially the composition of dark matter, but those are rather far beyond what I've been going into today.
Over here.
How do you decide what you're going to spend after you spent 13 hours looking at one thing? How do you decide, oh, there's something interesting out there? Do you just aim and hope, or?
So the question is, how do you determine what you're going to spend 13 hours staring at? What goes behind this?
You just name 10 things that you want to do with it.
Right, and certainly there are vastly more things that the astronomy community wants to do with James Webb than we will ever have time to do. And that's going to be a painful process, deciding what we do and what we don't do. For things like this, then you have to do a lot of pre-selection based on using less expensive time investments to find what the most interesting things are ahead of time. So for instance, that one galaxy, we looked at those fields with HST over a much larger area, first of all. So we had an idea what it looked like, what galaxies around it looked like. We knew it looked unusual. We looked at this galaxy with at least 2 or 3 other spectrographs in different ways as well, to confirm that it really was where we thought it was before we sunk this much time into it. And then once we started observing, we observed for 2 hours, so we were getting something useful and then kept going. But still, sometimes the best science is pointing towards a blank area of the sky and just seeing what you get.
Yeah, following up on this question about dark matter, is dark matter like non-baryonic stuff? Is that what?
Non-baryonic. I'm sorry.
No, if you repeat it, that's the non.
So the question was, is dark matter baryonic or non-baryonic? I'm talking about non-baryonic dark matter, yes.
Question down front.
What would be the incremental cost and trouble of having 2 James Webbs?
Well, I could go out on a limb and say that the cost of 2 would probably be less than twice the cost of 1.
Do we have a question over here? Yes.
I'm going to ask a question that's not really related with what you've been talking about tonight. I saw an article in the Daily Mail a couple days ago about what the scientists were referring to as fast radio bursts, which have been some kind of not communication, but some kind of interstellar that they've been able to.
So the question is about what are fast radio bursts?
Yeah.
Do you know what fast radio bursts are?
I personally don't know much about those.
And supposedly they've noticed this back from like 2007, and now they're investigating it.
I've heard of fast radio bursts, but I'm not a radio astronomer, so I really.
And they're insinuating that this may be some kind of extraterrestrial communication
Certainly an exciting hypothesis, but as I think I mentioned with the potassium flow stars, there's a whole lot of more mundane things I think we need to rule out first.
Have you heard of something like this?
I'm not familiar with that particular article, so I probably couldn't comment more on it.
We have a question over there.
This is just, I'm a PhD student at Johns Hopkins, and so I happened to read the Daily Mail article in question. So our current knowledge and understanding of so basically there are these really, really, really fast signals in the radio portion of the electromagnetic spectrum that pop up and go down too fast than other very strong radio sources that astronomers have studied throughout the years. So although with definitive proof, we can't rule out that it is aliens sending us directed radio emission, other things also can't be ruled out, like disruption events dealt with maybe a stellar mass black hole and an object, sunlight or larger object getting shredded by it. There is a few other transient events that might be in the parameter space that people are looking at. Only a few of them have been discovered, and usually when you discover they have occurred, it's a little too late to look at it with other instruments to kind of confirm what's going on with them. But we have honed down on one of them that it is occurring within a galaxy, and there's a whole host of astrophysical processes that can't be ruled out along with aliens. So,
Thank you.
Thank you. Question there.
The technology for your 3D spectrograph, what was the technology advance that has led to these? Is it a computational or a better grading?
So the question was what the technological advance was that led to the ability to do IFU spectroscopy. Part of it, computational advances have certainly helped with that, in the sense that you need to reformat the data into some form where you can process it more easily. But possibly it's also just been a gradual advance in manufacturing techniques. Part of it's also been an advance in the boundaries of our knowledge, where now we've surveyed large numbers of galaxies individually as point sources, and we're realizing that in order to understand more about them, we really need to start treating them not as point sources, but as the large extended objects that they are.
All right, there was one question online I'm trying to find. I guess it had to do with the scheduling of the telescopes and how far in advance the telescopes like Hubble and Webb are set. How long in advance?
So it depends on the telescope. So with ground-based telescopes such as Keck and the like, it's usually about 6 months or so in advance. With space telescopes, there's usually a longer lead time. With Hubble, the traditional cycle is you come up with an idea, put in a proposal. A few months after that, a committee will decide who receives time. A few months to a year or so after that, the observations will actually be taken. So it's roughly a year or so as lead time. Although for some special cases, it can be substantially shorter. Sometimes if you want to study transient events like supernovae, you don't have much warning. You can't put in a proposal in advance. I'm going to look there in 6 months, because you don't know that yet. So there's some capability of handling that as well, being able to follow up rare and extremely interesting things on a short time scale.
All right, last question here.
On one of your most recent slides, you had something that showed different materials, and one was methanol, ice, ammonia, ice, and I was wondering about the term ice, what that referred to.
Oh, that is an excellent question.
So the question was about ammonia ice and methane ice. What does ice really mean in that term?
So this is venturing outside my own area of expertise, but I would hazard a guess it's probably to do with what the state of the object is that you're looking at, rather than necessarily looking at it in a gaseous form. We're saying perhaps reflected features from crystals of solid ice in the atmospheres of these planets instead.
Right. Yeah. When astronomers speak of ices, it's not just water ice. Lots of different ices out there that especially in the clouds of the planetary system, the giant planets. All right. Hold on before we thank our speaker. Are you Irini? Yes. If you would like to go across the street to the observatory, meet her. Where are you going to meet? You want to come down here, over here where people can find you? All right. She will take you across the street for the Maryland Space Grant Observatory. Next month, Mia Bovel will talk about the Harvard computers and all the spectroscopy of stars that he skipped over tonight. And ladies and gentlemen, let's give another big hand for David Law.
Thank you.